Welcome to this explainer. Today, we're going to completely unravel the physics and, more importantly, the practical measurement techniques behind these incredibly elusive emissions. We're going to take a journey from the highly predictable, well-behaved world of the far field and step directly into the absolute chaos of the reactive near field. Because, let's face it, this is where the real diagnostic work happens, and understanding the physical laws governing this space is basically the ultimate key to saving your designs. All right, let's dive right into this. Our roadmap for today: 1. The near-field boundary. 2. Dynamic wave impedance. 3. Probing E and H fields. And 4. Probe calibration and metrology. Okay, Section 1, the near-field boundary, transitioning from the far field. So, to really grasp the near field, we first have to understand what it is we're leaving behind. Let's start our spatial journey out in the stable, radiating far field, which you might also know as the Fraunhofer region. Out here, safely distanced from our radiating source, the electromagnetic field behaves beautifully as a plane wave. The electric field, E, and the magnetic field, H, they travel in perfect lockstep. They're orthogonal to each other, orthogonal to the direction of propagation, and their power drops off at a super predictable linear rate of 1/r. But as we start walking backward, getting closer and closer to our emitting circuit board, this perfectly orderly relationship completely falls apart. Boom, right here. This is the mathematical transition boundary. Straight out of Maxwell's equations, the dividing line between that well-behaved radiating far field and the chaotic reactive near field happens at a distance roughly equal to the wavelength, lambda, divided by 2 pi. Or, for us practical engineering types, we usually just simplify that to lambda over 6. So cross this invisible line, meaning you get closer to your board than lambda over 6, and you are officially inside the near field. Out here, the fields absolutely do not decay at that simple 1/r rate anymore. Instead, the reactive near-field components drop off incredibly fast, at rates of 1/r squared and 1/r cubed. The energy isn't just radiating away. A lot of it is just being stored and bounced right back to the source. Moving on to Section 2, Dynamic Wave Impedance, the divergence of E and H. So as we push past that lambda over 6 boundary and go deep into the near field, something wild happens. The electric and magnetic forces just completely decouple. They stop moving in lockstep, and they often fall totally out of phase. Depending on the physical geometry of your traces and components, one of those fields is going to completely dominate the other, creating a highly chaotic, highly reactive environment. And that brings us to our absolute cheat code for understanding this space: wave impedance, or ZW. It's actually pretty straightforward. It's just the ratio of the electric field intensity, E, to the magnetic field intensity, H, expressed in ohms. Kind of like how Ohm's law relates voltage and current in a circuit, wave impedance relates the E and H fields in physical space. Figuring out how this ratio shifts is literally how we decode the physical source of an EMI problem. To really put this in perspective, let's quickly look at the far field one more time as our baseline. Once you're out past that lambda over 6 boundary, the ratio of the E and H fields perfectly converges to a constant value, roughly 377 ohms. That's the intrinsic impedance of free space. Out there, it doesn't matter what kind of antenna or circuit generated the signal, the wave impedance has totally stabilized. But inside the near field, yeah, that 377 ohm number goes completely out the window. In the near field, the wave impedance is entirely dictated by the source characteristics on your PCB. If you've got a high-voltage, high-DVDT source, think of an unterminated trace or a switching node acting like an open wire, it generates a massive electric field. This is a high-impedance source, and it drives the local wave impedance vastly above 377 ohms. Conversely, if you're dealing with a high-current, high-DIT source, like a tightly routed power loop or an inductor, it generates a dominant magnetic field. That low-impedance source drags the wave impedance way, way below 377 ohms. Recognizing this divergence is basically how you figure out if you're trying to fix a voltage coupling issue or a current loop issue on your board. All right, Section 3, Probing E and H fields, the zero observer effect. Now that we've actually reached the physical source of the noise on our PCB, we hit a massive practical roadblock. How on earth do we measure these wild localized impedance swings and field intensities without actually altering the circuit itself? This brings us to what we call the zero observer effect. Think about it. If you try to measure a high-frequency switching node by physically touching it with a standard passive 10x voltage probe, you instantly inject several picofarad of parasitic capacitance right into that node. At high frequencies, that capacitive loading hits the circuit like a sledgehammer. It artificially drops the resonant frequency, dampens the voltage overshoot, and basically masks the exact physical behavior you're trying to diagnose. Non-contact near-field probes are the workaround here. Because they couple through space rather than making direct galvanic contact, they act as totally invisible observers, introducing zero capacitive load to your switching node. To actually capture these fields, we rely on a really cool duality of diagnostic tools. First, we have E-field probes. These are typically built as monopoles or exposed stubs that couple to the electric field perpendicular to the board, capturing the capacitive displacement current. They produce an output voltage that's proportional to the derivative of the node's voltage. Second, we have H-field probes. Structured as conductive loops, these rely directly on Faraday's law of electromagnetic induction. The time-varying magnetic flux coming off a trace passes right through the loop, inducing a voltage proportional to the rate of change of the primary current. Oh, and a well-designed H-field probe will also include electrostatic shielding to suppress any unwanted E-fields interference, making sure you are purely measuring that magnetic flux linkage. So we now have this voltage waveform on our oscilloscope, captured by our invisible observers. But here is the absolutely critical question. How do we actually know that raw voltage is telling us the truth about the absolute field strength? The probe is essentially just a transducer, right? And its sensitivity changes wildly across different frequencies. A 10 millivolt signal on your scope at 10 megahertz means something entirely different than a 10 millivolt signal at 1 gigahertz. Which brings us to Section 4, Probe Calibration and Metrology, Establishing the Truth. To turn this qualitative troubleshooting wand into a rigorous quantitative scientific instrument, we need to establish the truth of its transfer function. The secret decoder ring for this is the calibration factor, or CF. It is explicitly defined as the frequency-dependent ratio of the actual true field strength, say the z-axis magnetic field H sub z, to the measured output voltage on your instrument, V out. It's a complex valued parameter. And what makes the calibration factor so incredibly powerful is that this single metric compensates for the whole shebang. It accounts for the physical geometry of your probe, the losses in your coaxial cables, the gain of your preamps, all of it, across a broad frequency range. Once you have the CF, you can accurately work backward from that raw scope data to find the exact field strength on your board. So how do we actually find this magic factor? Well, traditionally, metrology labs use the substitution method. They stick the probe inside this massive, expensive TEM or GTM cell, which generates a perfectly uniform known field, and they compare the probe's output against a reference standard. While that's highly accurate, unless you have a spare room and a massive budget for a GTM cell, it's not exactly practical for a benchtop engineer. The modern practical alternative is the broadband grounded coplanar waveguide, or GCPW Microstrip line calibration method. This uses a precisely manufactured trace on a standard circuit board to create a known quasi-TEM field right there on your bench. Let's walk through how this builds into an incredibly efficient methodology. Step 1. You drive that calibration microstrip trace using a comb generator, which blasts a highly stable broadband pulse covering a massive frequency spectrum all at once. Step 2. You hover your probe at a precise height over the trace and capture a single time domain voltage waveform on your scope. Step 3. You run an FFT on that measured data and reference it straight against mathematically simulated 3D field data for that specific microstrip. By comparing the two, you can extract the complete system calibration factor across a huge frequency range, like from 10 megahertz all the way up to a gigahertz, all from a single fast measurement. Ultimately, this whole explainer isn't just about abstract physics or chasing academic precision. It is completely about practical survival in modern electronics. Mastering near-field metrology genuinely prevents critical EMC failures in high-speed circuit design. When you understand that lambda over 6 boundary, when you can dynamically track whether the wave impedance is high or low, and when you rigorously calibrate your non-contact probes, you totally transform EMI troubleshooting from this dark art of black magic into an exact, highly predictable science. You stop guessing, and you start measuring the true physical realities of your board. Which leaves us with one final thought for you to ponder as you head back to the bench. Armed with this new understanding of reactive fields, wave impedances, and invisible observers, ask yourself, what hidden near-field coupling is secretly compromising your next high-speed design right now? Until next time, keep exploring, keep probing, and always measure the truth.